Hello everyone, welcome back to Chemical Engineering and Aspen channel. As you know that we are focusing on the module of Chemical Reaction Engineering. So in this regard, we are bringing the lecture number 28 for our valuable viewers, which will be from the topic of isothermal design, which is chapter number 5 of the book Elements of Chemical Reaction Engineering by H. Scott Fogler, which we are following once we are covering this module. So today we will solve example number 5.4, which is related to the pressure drop in the reactors, and accordingly we will see how we can calculate, and at the end of that we will do some analytical calculations for it. So the statement is that plot the pressure drop in a 60 feet length of 1.5-inch schedule 40 pipe packed with catalyst pellet 0.25-inch in diameter. There is 104.4 pound per hour of gas passing through the bed. The temperature is constant along the length of the pipe at 260 degrees centigrade. The void fraction is 45%, and the properties of the gas are similar to those of air at this temperature. And the entering pressure is 10 atm. So we are given the length, we are given the schedule of pipe and pipe size. We are given the information about the catalyst pellet size. We are given the information about the flow rate, the temperature, void fraction, and entering pressure. Now we will be using these two equations in our process. This equation, which is P small p actually, is equal to P over P naught. That is the pressure ratio. That P naught is the inlet pressure, that P is the outlet pressure. If there is a difference between these two pressures, it means there is a pressure drop in the system. And that is equal to square root of 1 minus 2 beta naught L over P naught. And that beta naught is calculated with this expression. So we will see what parameters are given to us and what parameters we need to find out. So first is the calculation of pressure drop. We know that G is equal to mass flow rate divided by area. So accordingly, mass flow rate is 104.4 pound per hour, while that of cross-sectional area is 0.01414 square feet. That is calculated from the schedule of pipe and the pipe size. And accordingly, it is calculated as 7383.3 pound per hour square feet. Now for air at 260 degrees centigrade and 10 atm, we have said in our problem statement that the properties of gas are similar to that of air. So accordingly, the viscosity is 0.0673 pound per feet per hour. The density is 0.413 pound per cubic feet, and the flow rate, the volumetric flow rate actually is mass flow rate divided by the density. So accordingly, we get 252.8 cubic feet per hour as volumetric flow rate of the gas which is entering in the system. So from problem statement, we are given the particle diameter of catalyst as 1 by 4 inches or 0.0208 feet. The void fraction is 0.45, and G of C is a constant factor. We know that 4.17 into 10 raised to power 8 pound feet divided by pound force into hour square. Accordingly, we first come to this parameter, which is beta naught, and that is equal to G. We have calculated it. Rho naught, we know that as well. G of C, dP, we also know these parameter. Phi is the void fraction, we know this. Viscosity, we know this. dP, again we know, and G is known. So all the parameters are known in this expression. So accordingly, substituting the values, the value of G is 7383.3. Rho naught is 0.413. G of C is 4.17 into 10 raised to power 8. D of P is 0.0208. Void fraction 0.45. Again, same 0.45. 150 into 1 minus 5, which is 0.45. Mu is 0.0673. D of P is 0.0208. And 1.75 into 783.3. So then we say that the first parameter answer is 266.9, and the second parameter answer is 12920.8. We termed these as laminar and turbulent in the system, and the outer expression is value is 0.01244. Accordingly, it is calculated as 164.1 pound force per cubic feet, and again by the expressions and by the unit conversion, that 1 square feet is equal to 144 inches square, and 1 atm is equal to 14.7 pound force per square inch. So that cancel out with this, pound force cancel out with this. So accordingly, we are left with 0.0775 atm per feet or 25.8 kilopascal per meter. So that is the calculation of beta naught in the system. Now next we know P, which is the pressure ratio, that is equal to P over P naught is equal to square root of 1 minus 2 beta naught L over P naught. Now that P naught is 10, L is 60, beta naught is 0.0775, 2 is the same parameter, so accordingly we get P is equal to 0.265. That is the pressure ratio. So that means if we convert it, P is equal to P over P naught is equal to 0.265 or P is equal to 0.265 into P naught. So accordingly, P naught is 10 atm. So that expression will become 2.65 atm or 268 kilopascal. That is the pressure at the outlet of the reactor. That means that if you calculate 10 minus 2.65, the total pressure drop will be 7.35 atm in the system. As you can see here, that delta P is P naught minus P, 10 minus 2.65, and that is 7.35 atm or 744 kilopascal. Now for plotting, we know that V is equal to V naught 1 plus epsilon x, P naught over P, T over T naught. Now this is an isothermal system, so obviously T over T naught will be gone from here, and we say that epsilon is equal to 0 in the system, so that will be left with V is equal to V naught over small p. That P over P naught will be P, that small p, so V naught over P, and that P is equal to this expression 1 minus 2 beta naught Z or L over P naught. Now, for z is equal to 0, 10, 20, 30, 40, up to 60 with an interval of 10. Now, you can see simply you substitute the value of z here. You have already calculated the beta naught, that will be the constant term in the system. So, what is changing now? Initial is 10 atm pressure. Then, once you substitute the value of 10 here of z, accordingly the P will be 9.2. Then you substitute the value of 20, the P will be 8.3. And accordingly at 60, which we have done just now, the value is 2.65. And accordingly this V will change, which is V naught over P. We had calculated V naught in our previous slides, and that P, which is the pressure ratio, and that is calculated as 9.2 divided by 10, 8.3 divided by 10, 7.3 divided by 10. So accordingly we get V is equal to 253, 275, 304, and up to so on 955. So this is the plot. You can also do it in Excel as well. For rho of C, if we say that rho of C is 120 pound per cubic feet, to calculate the value of alpha in the system, that alpha is equal to 2 beta naught over 1 minus 5 A of C rho of C P naught. Beta naught is 0.0775, 1 minus 0.45, A of C is 0.01414, rho of C is 120, and P naught is 10. So accordingly, alpha comes out to be 0.0165 1 by pound or per kg, and that value is 0.037 in the system. Now this is the last part of today's lecture, and you can see here that we are representing the effect of pressure drop on pressure, concentration, rate of reaction, conversion, and volumetric flow rate. Now you can see on x-axis there is weight of catalyst, on y-axis in first term it is pressure. So once there is no pressure drop in the system, the pressure line will be the constant. There will be no change with the weight of catalyst on the pressure term. However, once there is a pressure drop, obviously with the weight, with the increasing length or with the increasing value, we can see the pressure is decreasing, and we have seen it in the previous slide once we talk about the pressure profile. Coming to the concentration profile, once there is a pressure drop, a term is added over here. Now this term is C is equal to C naught into 1 minus X if there is no pressure drop in the system. But once there is a pressure drop, this P over P naught will come. Obviously, this P over P naught will reduce the value of C naught. It means that once there is no pressure drop in the system, the value of concentration will be higher than once there is a pressure drop. Why? Because that P over P naught will reduce the value of that CA. So as you can see that when there is no pressure drop, the trend is a bit high as compared to the pressure drop. Similarly, with the increase in the value of C of A, the rate of reaction will be high, because the rate of reaction, which is minus RA, it is dependent on the concentration term. So high value of concentration, higher will be the rate of reaction. So obviously for no pressure drop, the rate of reaction will be higher as compared to that scenario once there is a pressure drop in the system. And once the rate of reaction is higher, it means the conversion will be higher. So as you can see in this trend as well, that once there is no pressure drop, you will get more conversion, while there is, once you include the pressure drop, there will be the less conversion. Obviously, you always have to consider the pressure drop because that will give you the realistic answer, and that we will see in our upcoming lecture as well. Now, with V is equal to V naught 1 plus epsilon x P over P naught. Once there is no P over P naught, V will be the constant term as we have seen in multiple scenarios. So once there is no pressure drop, no effect of change in length or weight, but once there is pressure drop, this V will increase as we have seen in our previous slide. As you can see here that V is increasing with increase in pressure drop in the system. So that's it from today's lecture. I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.